Assalamu alaikum. It's our eighth lecture of Advanced Electromagnetic Field and Waves. In this lecture, we will continue our topic, and that is boundary conditions for the electromagnetic waves. Okay, we already show you this boundary conditions in our previous lecture number 7th at the end. Now we will start again from boundary conditions. Okay, let's suppose you have two mediums, your medium 1 and medium 2. Your electric field is going into from medium 1 to medium 2. Okay, and there is a surface you can see. In this, you can see your incident electric field is E1 and your outgoing electric field is basically E2. Now what you have to do, you have to make rectangular components. Okay, rectangular components for this, make this and this is the normal, so it becomes E1n, and this is the tangential part, this becomes E1t. Okay, similarly you can see this is the normal part and this is the tangential part, so this becomes E2n, and for the case of 2 it becomes E2t. Okay, now we have to take a sphere on which we have to found our electric field. So we, as we already calculated in our previous lecture, and that basically equals to n cap. Okay, E2 minus E1 equals to 0. Similarly, we also derive this relation n cap H2 minus H1 equals to 0. Okay, we already derived this in our previous lecture. Okay, so we can conclude from these relations that in non-conducting medium, your tangential components are equal. Okay, for the case of E and H, your tangential components are equal, or you can say continuous, because E1t now equals to E2t from this, and H1t equals to H2t from this equation. Okay, so we can conclude that in non-conducting medium, your tangential components are equal. Okay, for the case of E and H. Similarly, let's find for the case of D and B. Okay, how we can find for the case of D and B? As you know that E is equals to epsilon E1. Okay, basically you know that your D is equals to E and epsilon, so this we already know. E1t equals to E2t. When we multiply it, this from this side, E1 epsilon 1 multiply, and from this side we have to multiply by epsilon 2. After multiplying epsilon 1 and epsilon 2, you can see this epsilon 1 E1 becomes D1, and this epsilon 2 E2 becomes D2. Now here we multiply by E1 epsilon 1, here we multiply by epsilon 2. When you multiply both equations by different numbers, your equation never equals. Okay, that's why your D1 now not equals to D2. If you multiply both equations by epsilon, okay, then it should equal, but we don't have to multiply by same, because then it not becomes D1 and D2. Okay, so in this scenario your D1 not equals to D2, so we can conclude that tangential component of D field are not equal, or you can say not continuous. Okay, similarly for the case of H, here you have to multiply by mu1 and mu2, here mu1 and here mu2, because you know that mu1 H becomes B. Okay, whereas mu2 H2 becomes B2. Again you multiply here by mu1 and here by mu2. Now you can conclude your B1t not equals to B2t. So you can conclude that in both case of D and B, your tangential components are not equal, or you can say that not continuous. Okay, we checked tangential components for E and H that are continuous and equal. We can check for D and B that are not equal and not continuous. Now let's check normal components of all these, like E, H, D and B. Now let's check their normal components. Okay, so to check normal components, we have to use by using Gauss's law. Okay, we know that Gauss's law is basically equals to D dot dA equals to 0 for the case of electric field, and Gauss's law for the case of magnetic field, we know that B dot dA equals to 0. Okay, with whole surface integral. If you open this dA vector, you will get n cap dA. Okay, because when you open a vector, you have cap, okay, with their magnitude dA. Now you have to draw the same figure as you drawed here. Let's now draw for the case of electric field again, but now because we are checking the normal component, okay, so we have to instead of this sphere we have to use a surface, and that surface has a perpendicular in two medium is n2 cap and in one medium is n1 cap. This is the normal component of this sphere, okay, surface you can say. Again you can see your electric field D is coming from one medium, it going into another medium, that is 2. So you have to make rectangular components like this and like this and this. This is the normal, so it becomes D1N, and this is the tangential, so it becomes D1T. Similarly for D2, it is the normal, so it becomes, okay, D2N, and this becomes D2T. So this equations now becomes equals to because you can see your tangential parts are becomes equals to 0, this and this, only you have the normal parts in this scenario. So d1 and basically minus d2n equals to 0, so you can conclude d1n equals to d2n. Similarly, you can draw a similar diagram for the case of B, and you will conclude your answer B1n minus B2n equals to 0, or you can say B1n equals to B2n. Means that your D and B fields in case of normal components are continuous, or you can say are equal. So as I wrote here, normal components of D and B field are equal and continuous. Now let's finally check for the case of E and H with normal components. Okay, we already know that d1n minus d2n equals to 0. When we multiply this by epsilon, you know that d is basically equals to epsilon and E. So for d1n it becomes epsilon 1, and E1n. For d2n it becomes epsilon 2 and E2n. Now you can see epsilon 1 multiplies here and here epsilon 2. Two different things are multiplying with on both sides. So you can conclude this is not equal. If both have same multiply factor like epsilon and epsilon, then you can say this is equal. But if they are different, so E1n not equals to E2n. So you can conclude normal component of E field are not equal or not continuous. Similarly, take this B1n equals to B2n, okay, and you know that B is equals to mu H. For the case of B1n it becomes mu1 H1n. For the case of B2n it becomes mu2n H2n. Okay, so you know that again mu1 multiplies here and mu2, so you can say H1n not equals to H2n. So we conclude that our normal components of B field are also not equal and not continuous. So let finally generalize these all equations I wrote here like boundary conditions across the interface of two dielectric mediums. This is medium 1 below this, and upside is the medium 2. So what are your final boundary conditions is this: your tangential component of electric field and magnetic field H is continuous or equal. These are two conditions we have, and other two conditions which we have is the normal components of D field and the normal component of B field are all continuous. Okay, so E1t equals to E2t, H1t equals to H2t. Similarly, D1n equals to D2n, B1n equals to B2n. So these are the four boundary conditions we will left off, and we will use this in solving problems. So the main point is that in problem, how many number of unknowns are given to you, you have to use that number of boundary conditions. If there are two unknowns, then you have to use two boundary conditions. If there are three unknowns, you have to use three boundary conditions. If there is one unknown, so you have to use one boundary condition. So you can say that number of unknowns equals to number of boundary conditions which you required. Don't use many boundary conditions. If there is only two unknown and you are using three boundary condition, this is excess of doing problem. And if there are two unknowns and you are using to solve by one boundary condition, this is again short of solving some problem. Either you will get your answer, but your answer is not specific. Okay, so that's why if there are two unknowns, you have to apply two boundary conditions. If there are three unknowns, you have to apply three boundary conditions, similarly, and so on. So these are our finally boundary conditions, these fours: 1, 2, and 3, 4. Okay, this is all about our boundary conditions. Okay, so let's move towards the next topic of today's lecture, number 8, and that topic is basically refraction of electromagnetic wave. Okay, so what is basically reflection and refraction of electromagnetic waves? You already know the concept of reflection and refraction. Okay, so let's suppose again you have to consider two mediums. Okay, this is your medium 1 and this is your medium 2. This is your boundary. You can see this line is basically the boundary. In medium 1, it has epsilon 1, it has mu 1, and it has z1. Z1 is basically not coordinate, but is this capital Z is basically the impedance. Okay, while in case of second medium, it is epsilon 2, mu 2, and z2. Okay, so let's suppose your electric field is okay going into the x direction. This is my coordinate which I am taking x in this. Okay, let my electric field in x and my wave is propagating in the z direction. Okay, I'm taking these coordinates, always remember for this problem. Okay, for this concept. So my electric field into the x direction, because my electric field is coming, so in one medium it's incident, so that's why I denote it as EI, and my wave is propagating into the z direction, so I wrote it as KI. So if my electric field into the x direction and my wave propagation is in the z direction, so please tell me where should be the H field, means where should be the direction of magnetic field. Okay, please tell me. You have to tell me in the comments. Okay, where is the direction of the magnetic field? Okay, as I told you that electric field, magnetic field, and wave propagation are always perpendicular to each other. So if your electric field in x and your wave propagation in z, so your magnetic field is always into the y direction. Yes, you are right, but there is another concept. As it is in y direction, please tell me either it is inside or outside. You have to tell me. This can be simply checked by the right hand rule. Let me tell you. You have to align your fingers in the direction of electric field. So as my electric field in the x, so I just align. You can see x axis. Now you have to curl your fingers into the next coordinate. So x, you have to curl your finger into the y. So where is y? Here or here? Yes, here. So I curl my finger this. My erection of thumb will denote the direction of magnetic field. So it is outward, you can say outward of this. Okay, this board or this page, or either you can say. Okay, but if y is going here, so I will use this. But here is my z component, which is the wave propagation. So y must be here in this side. So this is alignment of the electric field. I have to curl my finger in the direction of y. My thumb will show in the direction of h. So my h is basically denoted by dot. Dot means out of the page. Okay. So this is how you can check. So this is electric field is going incident EI, having wave propagation which is KI, having okay, magnetic field HI. Okay, it strikes this boundary. After striking with this boundary, you know that some of the wave transmit and some of the wave reflect back. So the transmitted wave is denoted by ET and having wave propagation KT, and your reflected back wave, now because it reflect back, so their wave propagation now reflects. So you can see here ER, which is the reflected electric field, and here is the wave propagation KR, and here is the H. But now please tell me, where is the direction of H? You can see your, you can see here your electric field is already into the X direction, and this is in Y, and your what is in the magnetic field. So let's use again this concept. So you can see again I align first of all my fingers in the direction of electric field, as you can see this. Now I have to curl my finger in the direction of Y. Here is Z. So I cannot curl my fingers in this direction. I have to curl my fingers into opposite direction. But I cannot, okay, curl. So I have to move my hand. So you can see this is in the alignment of electric field. Now I have to curl my finger in the direction of Y direction. So this thumb will shows me the direction of magnetic field. So you can see it is into, you can say inside the page or inside the board. That's why I showed here with the cross sign, means into the page, okay, inside the medium, inside the page, or you can say this board, the direction of basically the magnetic field. So this is just the illustration how you can show by simply drawing their figures. Now you have to write their equations, your equation of electric field and magnetic field for the case of incident. Similarly, you have to write electric field and magnetic field for the case of reflected. Then you have to write the similar case for transmitted electric field and magnetic field H. Okay, so let's start off writing their wave equation. First of all, let's start with the incident wave. Okay, so this is, let's write incident wave for the case of electric field first. Okay, so incident wave, so it is denoted by EI as showed here. EI is equals to E naught, which is the constant, as you know that your electric field into the X direction, so that's why X cap here. Okay, now e power iota, which is already okay, K1Z. Yes, your wave is propagating in the Z direction, that's why it becomes Z, because it is in the first medium, that's why I wrote it as K1. Okay, now you can see here minus iota omega t, which you all know that omega is basically angular frequency. Okay, this is basically the wave equation of electric field for the case of incident. Similarly, you have to write for the case of H. So this is the direction of K, wave propagation, but where we find the direction of Z? Yes, in the Y direction and inside, sorry, in this outside. For the case of outside of the page, you have to take positive, so that you can see positive Y direction H naught, which is the wave amplitude constant. I basically it's the incident, and e power iota k1z, again your k direction into the zy iota k1z minus iota omega t. So this is the basically the electric field and magnetic field in case of incident. Okay, now you have to write for the case of reflected. Okay, so E reflected is now basically denoted by EF. Okay, reflected, again it's equal this scenario, sorry, this scenario. Okay, again equals to E naught, which is the amplitude constant, and X direction, because you see again your electric field is or in the X direction, so X cap here. Now E power, now you can see this is in Z direction, but now you can see this is in Z direction, but your wave is propagating now opposite. You can see in incident wave is propagating this, but after reflection wave is propagating in opposite direction. That's why it is going into the opposite direction. Now you have to use minus sign with the propagation of wave. Now it becomes minus iota k1z minus iota omega t, as it is because there is no change in the time. Similarly, for the case of magnetic field, in this magnetic field is inside the page, cross sign, as we find okay in few minutes before. Okay, as we find it that in this scenario, in the case of reflected, your magnetic field basically into the page inside. Okay, as it's inside and it's in the y direction, so for the case of into the page we have to use minus sign. So minus y cap h naught divided by z naught 1, because we know that basically the formula of h is equals to h naught divided by, okay, z naught. This is the formula, okay, so must we have to use. So here h naught divided by z naught in first medium, so z naught 1. Here is also h naught divided by z naught 1, here I wrote, okay, you can see. Similarly e power, because again your wave propagation into the negative, so you have to use minus iota k z, z because into the z direction, minus iota omega t as it is. Now let's write our equations of electric field and magnetic field for the case of transmission. So you can see in this scenario, you can see your wave is going, your electric field into the x direction, your wave propagation to z direction, no problem. So similar et becomes e naught t x electric field e power iota k2. Now we have to use k2 because now you are in second medium, okay, k2 z because your wave is propagating into the z direction, minus iota omega t as it is because there is no changing into the time. Similarly for the case of magnetic field, your magnetic field again in this scenario is out of the page, okay, you can calculate by formula which I told you, okay, in this video illustration. So ht becomes equals to y cap h naught divided by z naught, which is the formula of this, and e power iota k2 z, k2 because we are in second medium, and z because your wave is propagating into the z direction, minus iota omega t as it is because there is no changing in time. So this is the initial of electric and magnetic, this is the reflected of electric and magnetic, and this is the transmitted of electric and magnetic field, okay, waves. Now we have to check their tangential components and we have to find their transmission coefficient and reflection coefficient. To find the transmission and reflection coefficient we have to use tangential components, okay, as we know that our first boundary condition, you know that e1t equals to e2t, e1t equals to e2t. Let's solve at z equals to 0. So at z equals to 0, e1t, where is e1t? This you have to put z equals to 0 here, here and here, all this, and you have to apply rho and wave equation. So when you apply z equals to 0, so it becomes, and taking, okay, it becomes 0, e power 0 1. So you ei basically now equals to e naught, okay, e naught x cap. When you put z0 here, again e power 0 1, you will only left with ef basically equals to e naught f x cap. Similarly here e naught t x cap, this becomes 0. So x cap cancels with all, and you will get your final equation is e naught I plus e naught r, because these two are in the first, okay, medium, equals to second medium, which is e naught t. So this is equation number A. Okay, how many unknowns are in this equation? E naught I is given. There are two unknowns, E naught R and E naught T. If there are two unknowns, please tell me how many boundary conditions we have to use in this problem. We have to use two boundary conditions. First we already used, and now because there are two unknowns, these two, now we have to use another boundary conditions. So we have to use tangential boundary conditions, okay. So we are using h1t now equals to h2t. Here I am using, again you have to apply for z equals to 0. So for z equals to 0, again e power exponential term e power 0 becomes 1, here again 1, here again 1. You will only left with y cap h naught I by z naught 1 minus y cap h naught 1 by z naught 1, here y cap by h naught t divided by z2, okay. So this you will only left with this, y cancels with y, here is also a y cancel, and you will only left with this, okay, this. Now you have to this is your equation number B, because we need E naught R, which is the one unknown, E naught T, which is the another E naught. So you have to solve this equation A and B. So let's add both equations. So you can see this E naught R plus cancels with this minus E naught R. You will only left with E naught I plus E naught I becomes 2 E naught I, and you have to sum up these two, you will get final this. And because we have to find the transmission coefficient, and transmission coefficient is basically, we know that E naught t divided by E naught I. So you have to solve this equation for E naught t divided by E naught I. What you have to do, just you have to move E naught I in denominator of E naught t, and you have to move this to the other side. Only just mathematical substitution, you will get your final transmission coefficient E naught t divided by E naught I, and that is equals to 2z2, which is z divided by z1 plus z2, whereas z1 and z2 are the impedance in one medium and in two medium. Similarly, at last you have to find the reflection coefficient. Okay, so to find reflection coefficient means you have to find E naught r by E naught I. What you have to do, here one thing is given, E naught I is given. Let find E naught t from this equation and put E naught t in either A and B, and this is my first equation. So you can see E naught I plus E naught r. I substitute E naught t from this equation, and I put E naught t in first equation here. Okay, now I have to solve this equation for E naught r divided by E naught I. After substituting, you will get your final reflection coefficient, and that was equals to z2 minus z1 divided by z1 plus z2. So this is the reflection coefficient of the electromagnetic wave. And when you will sum your reflection coefficient and your transmission coefficient, you will get your, okay, total answer, which is the let's suppose your incident must be equals to final. Here conservation observe, okay, here conservation obey, there is no violation in conservation. Incident is always equals to reflection back. Okay, when you sum up the transmission coefficient and reflection coefficient. So this is all about our lecture number 8 of advanced electromagnetic field and waves. In this lecture, we thoroughly discussed the boundary conditions of electromagnetic field and waves. What are their boundary conditions? We check for D, we check for again E, and similarly we check for B and H, their boundary conditions. And then we move towards the next topic, and that topic is the reflection and refraction of electromagnetic waves. Okay, and then we find their tangential components, and finally we discuss their, okay, transmission coefficient as well as their reflection coefficient. So that's all about our lecture number 8 of advanced electromagnetic field and waves. We will cover more lectures for this course. Okay, so that's all for today. Thanks for watching. Stay tuned with us. Allah Hafiz.